Alright, we're back into section 7.4 on vectors. We talked about considering vectors as a line segment on the plane, and then we started talking about how we could also think of vectors in a different manner. So I've got a vector drawn out here, vector v, which I'm going to call vector pq. The initial point is p, the terminal point is q, and I'm looking at how this point changes from p to q as it's moving along this line, that it's displaced a units horizontally and it's also displaced b units vertically. So what we're going to do here is we're going to consider those displacements as part of this vector, and we're going to write it as vector v is equal to horizontal displacement, vertical displacement. And we're going to call this component form. Now in some books they use parentheses instead of these angle brackets, but I like these guys because they don't look like an ordered pair that you would be if you were graphing a point on the plane. So the component form of a vector, let p be the ordered pair, see parentheses, x1, y1, and let q be the ordered pair, x2, y2, be points on the plane, and let vector v be equal to pq. The component form of vector v is given by, see, this is the horizontal displacement, this is the vertical displacement. Notice that you're taking the tail, tip minus the tail, tip minus the tail. This x value minus this x value, this y value minus this y value. So it's tip minus tail to help you with that. And you can write it in component form, which we're going to do here in just a second. Now if you sketch the graph of a vector, now this one's not in this particular form, but if you sketch the graph of a vector so that the initial point is at the origin. So if I needed to do that, I would have to take this vector and bring it over here. If you do that, so that the terminal point is at the point AB, because now, picture it, let me use a different color here. Hopefully I didn't give something that's perfectly lined up, so that this is, hang on a second, this is 7.5 inches. Let's see, 7.5 inches. I'm trying to get this all lined up. I'm doing a terrible job of it here. I would have, well, see, it doesn't look very parallel, does it? No, and I didn't do a very good job here. So if I rewrote this vector and moved it here so that the initial point is at 0, 0, then if you're going a units to the right and b units upward, if that's your horizontal displacement, your vertical displacement, then so that the terminal point is AB, then we say the vector is drawn in standard position. That means the initial point is at the origin, and we can say that the vector in component form is the vector AB, because then it would be like a minus 0, b minus 0, because this being 0, 0 here. So let's try an example. Let me get back to my other marker. Suppose that vector v has an initial point of -4, 5 and a terminal point of -1, 12. I find vector v, this is part A here, it says find the component form. I find vector v here by doing tip minus tail. So the tip is the terminal point, that would be -1, 12, minus the tail, that would be -4, 5. So what I have here is -1 minus a -4, that's plus 4, 12 minus 5, and I get the vector 3, 7. Now it says if vector v is placed with its initial point at -2, -7, what's its terminal point? Now remember, this means a vertical or a horizontal displacement of 3 positive, so I'd be to the right, and a vertical displacement of 7, that would be 7 up. Not the soda. Anyway, so if I start at -2, -14, and from this x value I move 3 to the right and 7 up, I'm going to get the terminal point to now be 1, -7. Now you say, well, I can't really picture that. Just get a piece of scrap paper, draw out your set of axes, graph these 2 points, draw your vector, graph this point, and then do what I do as far as a parallel in the same direction and the same length, and see if you don't get 2, 1, -7. Alright, now, next thing up. Not only can we write vectors in component form, again, horizontal displacement, vertical displacement, but we can, in component form, we can add vectors, we can subtract vectors, and we can do scalar multiplication with vectors, which is a heck of a lot less hassle than trying to do it geometrically. This is referred to as doing it algebraically when we're using component form. So we're going to do an example here. Now before we do, the operations of vectors in component form, let vector v be a sub 1 b sub 1, vector w be a sub 2 b sub 2, and let c be an element of the real numbers. C is a constant. So vector addition, if we're adding vector v and w, all you're doing is adding the horizontal components, the x's, and the vertical components, the y's. And then writing it as the in the component form there with the angle brackets and such. Subtraction, you're just subtracting the horizontal and the vertical components respectively. And for scalar multiplication, even simpler, it's as if you're distributing this constant c, which is not part of the vector, throughout the vector by multiplying it times both of the components there. So we'll try an example here. Now that's a little weird. You just need to take the time to think about this and take some time and to kind of picture these out on a plane by graphing some points. It'll help a little bit. So in this case, we're going to add vectors r and s. R is -3, 10, and s is 12, -7. So this becomes -3, 10 plus 12, -7, which becomes -3 plus 12, 10 plus -7. So this becomes vector, hopefully you can still see this, -3 plus 12 is 9, 10 plus -7 is 3. And I get vector 9, 3. Yep, I think that's still on the screen. Now we'll subtract them. Now again, vector addition is commutative, whether it's in geometric form or if it's in algebraic form, component form. Notice here, you would just subtract or add them in the opposite order, and addition is commutative. Now not so with subtraction, just like with subtraction of real numbers. This becomes vector s, which is 12, -7, minus r, which is -3, 10. So this becomes 12 minus a -3, -7, minus 10. And this becomes 15, -17. And that's your vector. 3 times vector r means 3 times the vector -3, 10. And as you can see here, we're going to multiply this scalar times both components of our vector, and we're going to get -9, +30. See how much simpler this is? You don't have to draw, you don't have to measure stuff out. It's a lot more convenient. This guy here, you're adding 2 vectors, but you're adding scalar multiples of 2 vectors. So this is going to be -2 times s, which is 12, -7, plus 5 times vector r, which is -3, 10. So this becomes, now first we do the scalar multiplication, this becomes -24, +14, this becomes -15, 50. So now we just add, we just did scalar multiplication here in both of these. Now we add the components here, the x components, or the horizontal components, that's -39, and that's 64. And there is the sum of those 2 scalar multiples. Now, I don't know if you can really appreciate this unless they ask you to take this kind of work here and to actually do this using the geometric method of adding, the geometric method of subtracting, and scalar multiplication. You would have to put your vectors most likely in standard position, so you'd be using the parallelogram method, and it would be a bit of a hassle. This is much more convenient, and hopefully easier for you to understand as well.